Hello, I'm Yehan Liu. Welcome to my Lab6 report about magnetic braking with Faraday. In this lab, we investigate how a falling magnet induces current in a conductive tube, slowing its fall. This phenomenon, known as magnetic braking, is a result of Faraday's law. We compare real-world observations to a computational model simulating the magnet-tube interaction. And we use Faraday's law to relate a change in magnetic field to an induced current. The resulting current produces a magnetic field that opposes the magnet's motion. Newton's law helps us model the forces and motion of the magnet. And here are some equations involved. First is Faraday's law. We use it to relate a change in magnetic flux to an induced EMF in the tube. And also the Bauer-Savart law. We use it to calculate the magnetic field produced by currents in the rings. And also the equation for magnetic dipole field. We use it to model the field produced by the falling bar magnet. And here are the two models in the lab. First one, the experimental model. We dropped a bar magnet through an aluminum foil tube and recorded the fall using a smartphone. The time it took to pass through was measured and averaged across 5 trials. And the second one, the computational model. We modeled the magnet as a magnetic dipole and the tube as a stack of conductive rings. The simulation calculates induced currents and resulting magnetic forces based on Faraday's law and Newton's laws. Let's see the preview of the result. In the experiment, the average fall time was 1.288 seconds, while in the simulation, the magnet took 1.261 seconds to fall through the tube. This close match shows that the model accurately captures the key physics of magnetic braking. Then let's see the experimental setup. In the setup, the system is a falling bar magnet, and the surroundings include the aluminum tube and the Earth's gravity. Initial values include the tube length of 0.27 meters, a magnet mass of 0.023 kilograms, and a magnetic moment of 3.65. We assumed the tube was symmetric, air resistance was negligible, and the magnet behaved like a point dipole. I dropped the magnet 5 times and recorded the fall using a smartphone. The measured times was 1.28, 1.24, 1.23, 1.18, and 1.51 seconds, so the average fall time was 1.288 seconds. Then here's the computational model. In the code, I defined the magnet's mass and dipole moment first. The magnet was visualized as a cylinder, and its dipole was aligned with a vertical axis to match the real setup. Then I created 2 functions, one to calculate the magnetic field of the dipole, and another to compute the rate of change of magnetic flux through each ring. These were used to determine the induced current at each position in the tube. Then the simulation loop updates the magnet's motion using Newton's second law. It calculates gravitational force, induced current, and the magnetic force from the rings. The position and velocity of the magnet are updated frame by frame. And here are the results. The experimental fall time was 1.288 seconds, and the simulated time was 1.261 seconds. The velocity time graph shows the magnet quickly reaches terminal velocity. Both models show strong agreement. The main difference is that the simulation ignores air drag and imperfections in alignment. Then some possible source of error include timing uncertainty from video frames and slight titles in the tube. Also, the simulation assumes a perfectly symmetric system and doesn't include air resistance. And the answer to the follow-up questions. For the first, what if? My answer is, if the tube's resistivity were reduced close to 0, the induced currents would be much larger. That would increase the opposing magnetic force, and the magnet would fall even slower, maybe almost float down the tube. Then the second question, if we added holes or slots to the tube, they would break the current path. That would reduce the induced currents and weaken the braking effect, so the magnet would fall faster. Thanks for watching.